Hello, welcome to my presentation today. I'm going to talk about my solution for the LINHAC student project competition, and the title of my project is Sequential Ice Hockey Event Generation using the Generative Adversarial Network. My name is Mohammad Fahim, and I'm from Linköping University. So, if we look at the contest problem statement first, here we have to generate or find the pattern events that leads to a particular outcome given the data. And for this project, we have used the Swedish Hockey League data that contains 20 matches provided by the SportLogic. Sports analytics can be used by the management level of a team to devise tactics. For example, in hockey, we can learn what steps to take for a particular outcome or determine player performance. In this project, we used hockey goal as a targeted outcome and generated sequential events and coordinates leading to that. Our solution for this problem was to learn a generative model. We have used TimeGAN, that is time series generative adversarial network, to capture the pattern of the original data and create a synthetic version of it. We showed the sequence of events that leads to a hockey goal from the synthetic data and plotted the coordinates of these events in a hockey rink. The reason behind using the generative model is that it can capture the pattern of the original data. Also, the generated data follow the same distribution as the original data. Again, sometimes the size of the original data can be small. For example, the data we are working with has only 106 goals, and it might be difficult for other machine learning method to learn pattern from the small amount of data. So, by using generative models, it is possible to sample unlimited amounts of synthetic data. Now for the training approach. First, we need to pre-process the data to make it compatible for the model, then use the TimeGAN to learn the pattern of the original data and make a synthetic version of it. Then find the goal events from the synthetic data and show sequential events leads to it, and finally plot the events coordinates. The architecture of the TimeGAN consists of 4 modules: the encoder, decoder, generator, and discriminator, and it used 3 different loss functions. These functions also help the TimeGAN to overcome mode collapse problem. We have implemented 3 generative models, TimeGAN and 2 variants of least square GAN, LSGAN, and evaluated the synthetic data generated from these 3 models by using PCA plots and with a sequence prediction task where we take the first 23 sequence as input and try to predict the next one. Here we can see the PCA plots of 3 generative models. Each dot here represents one sequence of data, and blue dot represents the original data, and the orange one is synthetic data. If a generative model learns the distribution perfectly, the blue and the orange dot would overlap. Here we can see that the TimeGAN learns distribution better than the other 2 models. We have also evaluated the synthetic data using a sequence prediction task. Given 23 sequences, predict the following sequence. We trained a recurrent neural network with synthetic data and test on original data. This process is called train on synthetic and test on real. We evaluated the mean absolute error and mean squared log error for the task, and TimeGAN shows better performance. We sampled 140,000 events using the TimeGAN and showed the heat map of goals using different bin calculation technique. In the upper figure here, we have shown the heat map of the goal where we have counted the goal events in each bin, and the lower figure here shows the heat map where we take the average of the goal events. The amount of goal in the original data was 106, but in the synthetic data the amount is more than 7,000. Here in the lower figure we can see, even though in the original data there is no goal in this area section, but synthetic data captures the pattern and generated these goal events. Here in the left figure we have shown the 4 individual sequence of events that leads to a goal. The G represents the position the goal is scored, and the right figure shows one individual sequence of events and their corresponding coordinates. These are all synthetic data. So the main contribution from us is the idea of using generative models and synthetic data for this project. Also, the approach we have implemented here is generalized. So it not only works with the goal pattern finding, but also can find other patterns such as zone entry. And to our best knowledge, this is the first work where synthetic data has been used in hockey analytics. And the code for this project can be found here. As our solution is generalized, it can be used to find different patterns for specific outcomes, and it is possible to sample unlimited amounts of data. And also there is event plotting and heat maps. So we believe these features might help hockey analytics to make a decision. Thank you so much for your time today.